Hi, how are you? Person. Hi. So it's another episode of my Kim Tutor thingy. So at this point in the semester, if you're taking General 1, you're chugging along, you probably with the chemical reactions still, probably aqueous reactions, probably just, maybe you're just about to hit gas laws. I don't know. We'll do those next week. If you're in General 2, you're probably still doing a lot of equilibrium, because equilibrium is the stoichiometry of General 2. Once you start, it just keeps on going. But this is the point in the semester where a lot of people start to feel kind of overwhelmed. The thing I always tell students about this point in the semester is don't let the chemistry throw you. Because a lot of the stuff we're talking about, it's stuff you're already familiar with. It's just got some chemistry stuff thrown on top of it. For example, you guys probably did percent composition. You know, that's just percent math. So is percent yield. All the calculations you're doing up to this point, it's probably just the unit conversion stuff from chapter 1. So if you understand that stuff, then you can let the chemistry throw you. Just because we're throwing chemistry on top of it doesn't mean it's got to muck things about. So to start with, we're going to do a little bit of solution stoichiometry, aka molarity in stoichiometry. And the thing to remember about molarity and the solution stoichiometry is it's more stoichiometry. So in the chapter before, most likely, it was in the chapter before. Now we did the chemistry conversions started out, you know, gram to mole conversions. Anytime you want to convert between grams to moles, you use molar mass. We did a few mole to mole conversions. You know, moles of A to moles of B. And for that, use either the formula, if you're not doing reactions. And when you get to reactions, then you look at the coefficients. But, you know, moles of one thing, moles of another. And we also did some conversions between moles to individual things, like atoms and molecules. And for that, we use Avogadro's number. So all the, or most of the calculations, if not all, depending on, you know, how you're taught it, in the reactions chapter is the same 3 conversions or types of conversions that you just do over and over and over again. And really, once we get deep into reactions, we don't really do a lot on the atomic level. So you're not going to do a lot with Avogadro's number. It might pop up every now and then, but for the most part, once you start to do stoichiometry and a lot of the chemical reaction type math, you're doing the same. You start off doing this basically the same 2 conversions ad nauseum. I guess I should put that in parentheses because it's not completely, doesn't completely go away. But we start to talk about aqueous reactions and aqueous solutions. We talk about stoichiometry a little more, and we talk about how to convert between moles to liters, which uses molarity, which is just the moles of solutes you have per liter of solution. So for example, let's say you got a reaction between iron 3 chloride and potassium sulfide. And you want to know how many grams of iron 3 sulfide you can make from 100 milliliters of 2 molar potassium sulfide. So first, notice it's a stoichiometry problem because it's got the same setup of any stoichiometry problem. How much of can be made from this much? You know, anytime you're going converting between some amount of one thing to some amount of another thing, that's stoichiometry. And no matter what measurements are given, the first step of any stoichiometry problem is to take what's given and convert it to moles, if it's not in moles already. So in this case, we are given a volume of a potassium sulfide solution, and we know the molarity. So remember that M stands for moles per liter. So 2 molar potassium sulfide means you have 2 moles of this stuff for every 1 liter of solution. So we start with the amount given. In this case, we're given 100 milliliters. Right, I'm going to cheat a bit and just convert that to liters, because most folks by this point know the little trick of moving the decimal over 3 places to go from mils to base. So to take that and convert it to moles, we use the molarity. So again, 2 molar means you have 2 moles of the stuff for every 1 liter of this stuff. So now we're in moles, just like we were in the previous chapter when we went from grams to moles using molar mass. Really the same thing. The only difference is you have to be told what the molarity is, because it could be any concentration. Molar mass, you can just pull from the periodic table, as we'll see in a minute. But yeah, just like in the previous chapter, I'm assuming it's a previous chapter for most of you guys watching this, the next step is to convert moles of what's given to moles of what you're looking for. And to do that, you look at the given equation. And according to our balanced chemical equation, for every 3 moles of potassium sulfide, we're going to get 1 mole of iron 3 sulfide. And now to convert moles of what we want to grams, since it asks for the amount in grams, anytime you go between moles and grams, use molar mass. And iron 2 sulfide, actually I'm sorry, it's actually 3 sulfide, isn't it? There we go. Iron 3 sulfide, its molar mass is 207.91. Yeah, I probably wrote the 2 because I was looking at that 2 at the time. Maybe. Oops, and it's that many grams per 1 mole. And that will give you 13.9 grams of Fe2S3. So, like I said, you compare this to any stoichiometry problems you did prior, the gram to gram type of stoichiometry. It's the exact same type of calculation. We've just added a new conversion factor to the mix. This mole to liter type of conversion. So now we're up to 3 different types of conversions. But other than that, if you compare that to any stoichiometry calculation we looked at before, or any one that I did in one of my previous videos, that sounds stupid. It's the same calculation. We just started a little different. We started with liters instead of grams. But the first step is to take what's given and convert it to moles. So looking at another example, let's say we have this reaction, which you might recognize as a neutralization reaction. And let's see how many milliliters of sulfuric acid is needed to completely react, i.e. neutralize 25 milliliters of 10 molar sodium hydroxide. So again, it's a stoichiometry problem. Convert this much of this thing to this much of this other thing in this reaction. So first step is to take what's given and convert it to moles. So we take the volume, and again, I'm going to cheat, because most folks know can convert milliliters to liters by this point. Plus, it saves me a little bit of space. So we convert that to moles using the given molarity. 10 molar means you have 10 moles of the stuff for every 1 liter. Now we convert moles of what's given to moles of what we want, which is, moles of sodium hydroxide to moles of sulfuric acid. And according to our equation, it's a 2-to-1 ratio. For every 1 mole of sulfuric, you're going to need 2 moles of sodium hydroxide. And finally, we're looking for a volume in milliliters. And actually, I forgot to give you the molarity, because like I said, you need that, don't you? Because you can't just pull it up from the periodic table. All right. Question should have read, how many milliliters of 3 molar sulfuric acid is needed to completely react, yada, yada, yada. So yeah, now that we have the molarity, again, remember the capital M stands for moles per liter. So you got 3 moles of the stuff per 1 liter. All right. So now to get the moles to cancel, that 3 moles has to be on the bottom. So again, that many moles per 1 liter. And that will give you 0.042 liters, or if you convert it to milliliters, 42 milliliters of sulfuric acid. So a couple things about this particular type of problem. There are 3 actually. One, just to reiterate what I said before, reiterate. It's the same type of problem. You know, stoichiometry, same type of setup. First step was just like the previous problem, convert what's given to moles. Then the next step was to do our mole-to-mole conversion, using our reaction. This time we wanted to convert moles to liters. But again, anytime you want to convert between moles to liters, assuming you're given the molarity, you can do that. For problems like this, people will also try to fudge in molar mass somewhere. Like I said a minute ago, the only time you really need molar mass is to convert between grams to moles. If you're not working with masses, if you're not starting with a mass, or you're not, there we go, or like in this problem, you're not trying to convert your units to a mass at the end, you don't need molar mass. So again, it's just the same, right now it's the same 3 conversions that we're just doing over and over again. 4 if you count moles to atoms / molecules, but we don't, like I said, we don't do a lot on the atomic level by the time we get into reactions, because we usually think about reactions on the mole scale. All right, and one other thing. For problems like this, about this time, people learn this thing called the dilution equation. The way I usually write it is M1V1 equal M2V2. You might see it written MI, VI, MF, VF. Some people will try to use this equation for this type of problem and just don't do it because you only use that for diluting solutions, which is another topic that we'll maybe talk about some other time. But you don't use it for a stoichiometry problem. Some people want to because they see everything they see molarity, milliliters, milliliter, molarity. Everything plugs. There's things you can plug in, but it's not going to work. It might work if everything's 1-to-1 stoichiometry-wise, like in this step. But yeah, this equation doesn't factor in stoichiometry. So you might get lucky and get it. It might work occasionally, if it's a 1-to-1 conversion for the mole-to-mole step. But yeah, just if it works once doesn't mean it's not going to work every time. So just don't do that. All right, so there we have it. There's solution stoichiometry. Again, it's just more stoichiometry. And when we get into the gas chapter, we're going to do a little bit more stoichiometry, add that to our conversion list. 4, 5 if you count Avogadro's number. When you get to thermochem, joules, we got 1 more. But yeah, at the end, by the time you get to that point, it's still the same types of conversions you're doing over and over again. And again, if you don't count Avogadro, you can count the number we do on the palm in one hand. If you want to count Avogadro's number, there's 1 more, but one little one. So yeah, don't let the chemistry throw you. If you understood unit conversions from chapter 1, it's the same stuff. I would even say it's easier because in the unit conversion problem, the unit conversion stuff in the first chapter, most of the problems you look at, they're just any old type of units. In fact, the first video I did for this shoe is, I just made up conversions. It's actually easier because the number of conversion factors we use, really seriously start to use in chemical reactions, again, you can, most of the time, you don't get any bigger than the palm of your hand. Palm of your hand, palm, I guess. Anyway, I misspoke. So anyway, that's the solution of stoichiometry. Right. So moving on to the General 2 guys. And sometimes I wonder how many of the General 1 folks stick around to see what we talk about in General 2. Or conversely, how many General 2 folks actually stick to the General 1 talk. Because in the YouTube description, I do click ahead or give you links if you want to skip ahead. Yeah, I imagine like the General 1 guys, they'll look at that and say, I have no idea what they're talking about. But just stick with it because you'll be amazed how much you learn. And you do learn stuff, I promise. Like for my guys, by the time we get to at the end of General 1, you know, some of the labs we do, you guys determine how many calories are in a peanut using a soda can. And you figure out the enthalpy change of a reaction, you know, using a styrofoam cup and a thermometer. And you think back to the very first lab that I do, it's, well, actually the first lab is just walking around. Actually, the first lab is just measuring volumes and maybe figuring out density, little density calculations, taking a metal, dunking it in water, volume displacement. And then you get to General 2, you're figuring out, you're measuring calories. Enthalpy change, something you didn't even know existed at the start of the semester. And you get to into General 2, you have the knowledge to be able to make a battery. So, which makes me wonder if the General 2 folks, when they look at the beginning of these shows, if they look and go, God, I can't believe I got stuck on the stoichiometry stuff. Man, I thought stoichiometry was bad then. Now we're doing equilibrium. Jesus Christ. But hey, speaking of equilibrium, we're going to talk a little bit about LeChatelier's principle. So LeChatelier's principle is really a continuation of the reaction quotient stuff that I talked about in the previous show, where it's a way to, you know, quantitatively, i.e. math, figure out how a reaction is going to have to shift in order to achieve equilibrium. LeChatelier's principle basically looks at it qualitatively, which says, you know, you got something in equilibrium. Again, you think of the whole balance idea. You got a system at balance. Last show, you remember the mind juggling. You know, chemical reactions want to maintain equilibrium, but things can happen to knock that equilibrium out of whack. LeChatelier's principle basically tells us how we can predict what will happen to that reaction if the equilibrium gets knocked out of whack, which way it's going to have to shift. Right. So, screen share. So, for most folks in General 2, we look at 3 different ways that you can make that equilibrium out of whack. First way we talk about is changing the concentrations. Concentrations. Oh, why does it? Concentration changes. So let's take the generic AB, give you a C type reaction. So you again, I keep forgetting the equilibrium arrow because I just got done talking about General 1. So again, both reactions are occurring at the same time and at the same rate, but under certain conditions, you can introduce more reactant or more product to the system. And according to LeChatelier's principle, if you increase the concentration of your reactant, or increase the amount of reactant, that's going to cause a shift to the right. And there's a couple of ways. Well, let me go and jump to the product side first. If you increase the amount of product, according to LeChatelier's principle, that'll cause a shift to the left. Like I said, there are some times where you can actually remove a reactant or product from the system. You might add something that will react with one of those chemicals, and if you react it, it gets removed. So if you end up decreasing the amount of reactant in your system, that'll cause a shift to the left. And if you decrease the amount of product, that'll cause a shift to the right. And there's a couple of ways you can kind of make sense of this. One is if you go back and look at the reaction quotient, which in this case would be reactant over product raised to the power of everybody's coefficient, which in this case everything's 1. If you increase the amount of, say, product, you add more C to the system, right? You're adding stuff to the top part of your ratio. So that's going to cause Q to get bigger. And if it was already at equilibrium, if you make it bigger, you're going to make it bigger than what the equilibrium constant was. So again, when equilibrium constant, or when your Q is bigger than the equilibrium constant, the system will react by, or respond, react probably the best word here, respond by shifting to the left. Likewise, if you increase the amount of reactant, you're adding stuff to the bottom part of your ratio. So that's going to make the overall ratio smaller. And if it gets smaller than K, then the system will have to respond by shifting to the right. Another way to think about it requires me to go back and mind juggle again. But if you like the idea of the two-pan balance, and some people do, so that's why I do this. Every now and then I'll still see people taking a test and they'll start mind juggling, as I like to call it. But again, if you think about equilibrium as being balance, now here's the reactant side, here's the product side. I hope I'm doing that on the right side for you guys. I think this is your left, your right. If not, just switch everything that I just said around. But yeah, if you add things to the reactant side, you think about a little two-pan balance, Lady Liberty, justice for all. If you add things to the reactant side, it's going to cause it to get too reactant heavy. So if it's too reactant heavy, you got to take things and move it over to the product side. It's got to move stuff to the right. Likewise, if you remove reactant, say you remove reactant and it becomes too product heavy. If it's too product heavy, now you got to take some of that product and move it over to the left. So it goes back to balance. And I usually don't have to do this high when I'm in class. So my arms are getting tired because I'm getting old. I can't do this anymore. All right, anyway, back to the word. If I can, oops, where'd it go? There it is. All right. So that's how you can mess with the concentrations and how LeChatelier says the system will respond. Right. Along those same lines, you can cause the temperature to change. Oops. And how the system will respond is going to depend on whether your system is exothermic or endothermic. So let's say you have an exothermic system. Remember, exothermic means heat's being released. So if heat's being released, it's essentially a product of the reaction. A and B react, give you C, and it releases so much heat. So if heat is a product of the reaction, if you increase the temperature, you're adding heat to the system. It's just like when you add any other product. And if you add in a product, it's going to cause it to shift to the left. Right. And if you cool the system down, you're removing heat. It'll be just like you're removing a product, and it's going to cause a shift to the right. But if it's endothermic, then heat is essentially a reactant of the system, because reactants A and B have to absorb so much heat to make your product or products. So now if you add heat, you're effectively adding a reactant. So adding heat, just like adding any other reactant that we said earlier, is going to cause a shift to the right. And if you cool it, you remove heat. Just like removing reactant A or B, the response is going to be a shift to the left. So it's basically an extension of what we said a minute ago, but it's conditional. It depends on whether it's exothermic or endothermic. But exothermic, endothermic determines whether the heat's a product or reactant, essentially. So when heat's a product, adding or removing heat will be like adding or removing any other product. If it's a reactant, when it's endothermic, it's the same effect as removing or adding any other reactant. And what's even more conditional is if you have a system that you can compress or expand the volume. And let's say, for example, you have A, and we're going to use 2B this time, to give you 2C. Basically, the way changes in volume work is that when you increase the volume, the shift is going to occur in whatever direction will increase the amount of gas. If you decrease the volume, it'll shift in the direction. Shift in the direction. Whoops. Yeah. No, very good. It'll shift in the direction that decreases the amount of gas. Dot, dot, dot. All right. So in the example above, we have a total of 3 moles of gas on the left, the reactant side, 2 moles of gas over on the product side. So if you increase the volume, in this case, the system should shift to the left to achieve equilibrium. If you compress your gas, if you decrease the volume, it's going to go to the right. But again, in this case, it's dependent on the stoichiometry of the system. So let's say, for example, same reaction, but now let's make B a solid. All right. So now you have a total of 3 moles of stuff, but only 1 mole of it is the gas. So again, the important thing here is how much gas is on each side. On the product side, we still have 2 moles of gas. So now when you increase the volume, again, whenever you increase the volume, it's going to shift in a direction that increases the amount of gas. In this case, that's going to be a shift to the right. If you compress or decrease the volume, the shift is going to occur in the direction, whatever direction decreases the amount of gas present. So it depends on the stoichiometry. And if you're curious as to why, this is basically the what, if you're interested in why, or if you need to know why. Really, again, we have to go back and look at the reaction quotient, but this time we'll look at the quotient with respect to pressure. So in this case, QP is going to be measured by taking the partial pressure of C, again, it's reactant over product, factoring in stoichiometry. It is a C here, over the partial pressure of A. And this is why we only look at the gases. Remember, solids and liquids aren't factored into the expression of Q. And for QP, you only use gases because that's what's going to affect your pressure. But you know, when you increase the volume, well, we'll do decrease first. I like doing that one first. You decrease the volume, and if you remember Boyle's law way back in General 1, that's going to increase the pressure because Boyle's law says those two are inversely proportional. One goes down, the other goes up. So the pressures of both C and A are going to increase, but since C is it's the square of C's pressure, the increase is going to be greater on the top half of your ratio, which means that this rate, the net effect means that Q is going to start to get bigger, and it'll eventually get bigger than K. And if Q is bigger than K, that's a shift to the left. If you increase the volume, that'll cause the pressure to decrease. But again, the top half is going to get smaller to a greater effect than the bottom half is. So the net effect is that, you know, when the bottom is going to start to get bigger, I mean, you know, the bottom part of your ratio is going to eventually get bigger than the top part of your ratio. You know, the net effect is going to be Q is going to start to get bigger than the original concentrations for equilibrium. And if that happens, that'll be a shift to the right. So again, remember, when, you know, starting off, easiest one to start off with is concentrations. You know, increasing the amount, which I guess it works for moles too, but I usually think of it in terms of concentration since we usually do solution chemistry. But again, if you add reactant or product, it's going to cause the equilibrium to get out of whack, and it's going to have to respond by basically shifting in the other direction. Temperature changes work the same way, but you got to factor in what side the heat is on. You know, is it released just on the reactant side or absorbed on the, released on the product side or absorbed on the reactant side? And for volume changes, you have to think about stoichiometry. But basically, the increase is going to favor an increase in gas. You just have to remember it's just gas that you're looking at, things in the gas phase. But other than that, it's just a matter of keeping those three things straight. All right, so that wraps it up for today. Next week, I don't know what I'm going to talk about. I don't know what I'm going to do when I hit the stop button. We'll see. So, I don't know. I'll think about next week later. I think I say that a lot at the end of these shows. But anyway, so that's it. Next week, we'll talk about some more stuff. If there's stuff that you want me to talk about, either next week or whenever you watch this, you can leave a comment. I think I'm going to start leaving the comment section open. I haven't left the comment section open for the YouTube channel just because I've seen what comment sections look like on the internet. I don't know. We'll see. If we stay civil, then yeah, if there's something you want me to talk about, just put it in the comment section. If it blows up gloriously, I'll shut her down. And I'll just do like I've been doing, where when I post the, when I do the initial Google Hangout link, you can do it there. But if you want to see when I actually do this stuff, just hit the subscribe button, and I usually do it about a week in advance, what time I'm going to actually do this thing live. So anyway, I am done because I'm babbling. That's usually a sign that I need to stop, right? All right, it's even worse in class. My students can attest to. All right, so now that's it for this week. and bye.